very much for the invitation to this very interesting conference. Thank you to what's left of the audience for staying to the bitter end. Since it's been a long week, I think I'll go a bit gently, and there will actually be almost no derived categories in this talk. It will be almost all lattice theory. So X is a smooth cubic in CP5, cubic fourfold, and there's the conference is about rationality, so let's talk about rationality for a little bit. You have the Clemens-Griffiths idea, which you heard about earlier, which is that if X is birational before, then you have this weak factorization, so you can blow up with smooth centers and then blow down and then blow up, and so on. And then, because you're always blowing up along points and smooth curves and smooth surfaces, the idea is that the motive of X, so if X is rational, then the motive of X comes from curves and surfaces from lower dimensional. So then, of course, the motive of P4 is just 4 points, essentially. And so the question is, what is the right so you want to try to turn this velocity into a proof. So you try to get a proof, and so which motivic thing should you use? So you could use the cohomology of X, and this was first, with its Hodge structure, this was first investigated by Hassett. You could try to use the derived category of X, because this blows up and down in a similar way and is in some ways better behaved. And this was pursued by Kuznetsov. And Zarkov and his collaborators have some approach along these lines too, using these Orlov spectra. But I don't have anything smart to say about that. Or you could use the class of X in the Grothendieck ring of varieties. And Galkin and Shinder have pursued this. You could also, in keeping with the theme of this conference, you could try to do something with the universal, with decomposition of the diagonal. But of course, you're not going to do it in the same way that it has been done yesterday in all the examples, because when you degenerate a cubic fourfold to a singular one, the singular ones are all either rational or cones. So if you're going to use decomposition of the diagonal on cubic fourfolds, you have to do something a little more clever. And Voisin has some partial results. But again, I won't really say much about that. So let me summarize for you some properties that X might enjoy.
So is it clear that all singulars are going to be non-rational?
The singular ones are all rational because you can project from the point, unless they're a cone. And then I guess the singularities don't work for your method. Right, so properties. So it may be rational.
By the way, there is another approach by Kurikov, which hasn't been ruled out yet.
Right, and this is essentially using Hodge theory. Right? Depends on some conjectures on, well, his first approach was using some conjectures about cohomology of surfaces that turn out to be wrong, but the approach isn't. There's something left. And this was depending on some conjectures about this Jordan-Holder theorem for semi-orthogonal decompositions, which turns out to be wrong, but maybe there's still something left in this approach. And this was depending on this thing that Morozov disproved over Christmas, that you heard about on Wednesday. So maybe you conclude that all cubic fourfolds are irrational because all these approaches fail. No, but there's interesting geometry in all of them. So x may be rational, and of course there are two examples. So examples, either x can be a Faffian of a 6x6 skew symmetric matrix of linear forms, and then it's rational, and this is due to Donaghy in the 80s. X can contain a plane and a certain other two cycles. So it could, for one thing, it could contain two disjoint planes, and Bert mentioned this. You could just project from the two planes. But there are many other two cycles that would do the job, and this is due to Hassett in the 90s. And well, the rest of them, we have no idea. I was imagining this board might be bigger. I'm sorry. You can think about, staying in geometry for a little bit, you can think about the variety. So F is the variety of lines on X. And so this is always a hyperkaehler fourfold, and its deformation equivalent to the Hilbert scheme of 2 points on K3. But sometimes it's isomorphic to the Hilbert scheme. This happens in the Boville-Donaghy example. Well, it happens generically in the Boville-Donaghy example. Let me say, instead of isomorphic, birational. Because birational hyperkahlers end up being non-separated in the moduli space. So birational is good enough. It might be birational to a moduli space of sheaves on K3 surface. And of course, the Hilbert scheme is a moduli space of sheaves, but we'll see that the second condition is a little bit weaker. And this is the same as isomorphic to a moduli space of Bridgeland stable objects. By this big theorem of Bayer-Macrì. So Macrì's gone. So these are equivalent. Actually, let me put some boxes here. So this is one condition. Here's another condition. You might have in the cohomology, let's talk about the cohomology of X. Let's look at the primitive H4. So H4 primitive of X is some Hodge structure with these Hodge numbers. You take out H squared, so it's 20 and one, not 21. This looks very much like, is it H2 of a K3? Was it into the right degree? Well, no, because this thing has signature 22, 20, 2, whereas this thing has signature 19, 3. But sometimes the primitive H4 of X contains as primitive subhodge structure, the primitive H2 of a degree of a case of a polarized K3. Bayer-Macrì of degree D. So that happens in both these cases and in many other cases that I'll describe for you in a minute. So this is the K3 surface turns up. So there's rationality, saying that the K3 surface turns up in the variety of lines. In thinking about the variety of lines, it may turn up in Hodge theory. And then the last thing is the derived category. So you have Kuznetsov's subcategory AX that you've heard about, and this is the orthogonal to 3-line bundles in the derived category of X. And always the Serre functor is the shift by 2, and the Hochschild homology and cohomology are the same as for K3. So this implies that if it were, I like to call it geometric, but that conflicts with Lund's terminology. If it were the derived category of a variety, it would have to be a K3 surface. Sometimes this AX is actually equivalent to the derived category of K3. And in both these cases, Kuznetsov has shown that this happens. So this is our fourth condition. So what are the implications? What are the expectations? So first of all, let me say that Hassett. I'll do conjectures and beliefs in dotted lines. So Hassett expects this. In his thesis, he asks, "Is it possible to have it on good authority that this is his expectation?" Kuznetsov conjectures that this is only if that, and then work of Galkin and Shinder they suggest that maybe it's that one there.
What's the difference between expects and conjectures?
Well, if you ask Brendan what he conjectures, he says, "Oh, no, I wouldn't conjecture that." But I don't know whether it's in writing, I guess. And I want to say just that they have a result that suggests this, but dependent on something that's now known to be false. So what else can we say? If Kuznetsov's category is coming from a K3, then it's very likely, so this is likely. I'm sorry, I was expecting to manage my board space a little bit. Let's say this way to this one here. This is likely. This is Kuznetsov and Markushevich. They showed quite a while ago that the variety of lines is not only, the variety of lines can be understood as a moduli space of objects in this subcategory. And by moduli space, I don't mean that there's some stability condition or that it represents a functor. I just mean that the variety of lines parameterizes some objects in here, and there's a universal family, and the Kodaira-Spencer map is an isomorphism. So if you could sort out the stability conditions, which nobody knows how to do, you could say that if this thing is a K3, then the variety of lines is a moduli space of Fritzl stable objects. So it's a moduli space in some sense, but there's stability to work out. Macrì and Stellari, who are both gone, they have some result about this when X contains a plane. What else will I show you here? So let me get into something that's proved. So I don't want to talk about this very much, but Richard Thomas and I proved that if this happens, then this happens, and we proved the converse generically. By which I mean this, I'll tell you in a second. This happens on a countable union of divisors in the moduli space, and in each one, this happens on a dense open subset. And then, so maybe I'll tell you about that now, and then in a minute I will tell you that this, if the variety of lines is birational to a Hilbert scheme, then it's easy to show. It's easy to show that this happens just by playing with some lattice here, playing with cohomology, and in fact, the theorem that I want to tell you about, in case you need to leave early, the theorem will be the newish theorem is that you can go the other way. Oh, sorry. No. That this cohomological thing happens if and only if the variety of lines is birational to a moduli space of sheaves on a K3 surface. Which it gives you this red arrow, but in a not so geometric way, in a lattice theoretic way. So let me show you a picture of the moduli space of sheaves, or the moduli space of cubics, which is, some of you know, of all cubics. And this is due to Voisin, Hassett, Laza, and let me really give you the full, for the students, let me really give you the whole lattice theoretic picture. So let's let L be Z21 with the pairing, the odd pairing of signature 21, 2. So it's 3 copies of +1 and 2 copies of -1. And so this is isomorphic to H4 of XZ with its intersection. And so in here I can pick some vector of length 3, which I'm going to call H squared. So they all live in the same limit. And I'm going to consider the map from C, which is the moduli space of cubics. You can just take all cubic polynomials, you take the open subset that give you smooth ones, and you mod out GL6. And I'm going to take the period domain D, which is a set of lines. I'm going to call them C times sigma in the projectivization of L tensor C. This sigma needs to satisfy some conditions, but at the end I'm going to mod out my automorphisms of L that preserve this H squared, the fixing H squared. And so what's the map going to be before I tell you the conditions? X is going to be sent to the line H31 of X inside of H4 of XC. So the conditions are these. I need sigma squared, sigma dot H squared to be 0, because of course H squared needs to be in H22. I want sigma squared to be 0, because there are no 6-2 forms. And I want, so together these give you some quadric in P21. And I want sigma bar to be negative. This is from the Hodge-Riemann bilinear relation. So you get some analytic open subset in this quadrant. Then you mod out this arithmetic group, and you come out with a smooth quasi-projective variety, which is a smooth PM stack, if you like that kind of thing. And so what do we know about this map?
Sorry, was the 23 as the 21, is that right? Or is that
23, thank you. So this is C22. Yeah, great. Thank you. And so what do we, so easy is that it's locally injective. Maybe this is due to rapport, but maybe not. Voisin's thesis. It's locally in isomer. So Voisin tells you that it's actually injective. And then Laza, in his thesis, and Lehn separately, and by his own method, it's do they describe the image? To describe the image, I have to tell you about Hassett's another Lattice divisors. Right, so if X is generic, then this Hodge group, H4 of XZ intersect H22 of X, is generated by H squared. H is the hyperplane class, of course. If X contains a plane, for example, then we get the lattice spanned by ZH squared NZ times the plane inside of here. And the pairing you compute is 3, 1, 1, 3. And the discriminant of this calculate is 8. So that gives you a flavor of what I'm going to say. So X is called special if it contains a surface that's not whose cohomology class is not a multiple of H squared. So it's not homologous to a complete intersection. So I'm going to define D sub B to be the set of all sigmas in B, such that if I take sigma perp intersect this lattice, it contains K, which is primitive of rank 2, discriminant D, and H squared is in K. And then I'm going to put CD to be the period domain for D intersect the actual image of this map. I've left myself much room now. Maybe I'll put it here. So the theorem. So here's the period domain. I'm going to take out D2, and I'm going to take out D6, and what's left is C. The image of the period map is exactly the complement of two of these divisors. So I should say this is an irreducible divisor, and it's non-empty if D is positive and D is congruent to 0 or 2 mod 6. And then we said that C8, so C8, this is cubics containing a plane. You have, maybe I won't write it, C12 is the next one, right? You want 0 or 2 mod 6. C12 is cubics containing a cubic scroll. C14, I don't want to suggest which ones intersect and which ones don't. C14 contains the Fathian cubics. This is generically Fathian cubics. They contain quintic deltatzos. But that's an open subset, it's a dense open subset of C14. And then Hassett proves Right. So now you understand very well.
So I'm sorry.
Yeah.
D6 corresponds to nodal cubics, and what D2 corresponds?
And D2 is these when you degenerate to the determinant of a 3x3 symmetric matrix of linear forms, it's the limiting mixed Hodge structures that you get in this way. Yeah. Semi-stable reduction. It's very beautiful. I have a dream in the back of my mind of writing a derived version of that result, but first we need to define limiting derived categories. This may never happen. And then Hassett's theorem, so you understand how the moduli space looks. Hassett, and I want to emphasize also, if you give me the equation of the cubic written down, 86x cubed, so we actually have some hope of computing h4 of xz intersect h2 cubed of x, right, by some arithmetic method. You count points over a few different fields, and you have some hope of determining what that lattice is, and so which of these divisors it lives in, or if it lives in none of them. So the Hassett's theorem, well, let me say it this way. We're interested in when the primitive cohomology of X contains the primitive cohomology of a K3 surface of degree D. And so you see, just by, so this has dimension 20, this has dimension 19. So just by taking its orthogonal, you get some sublattice of H4 of rank 2, and if you know a little Nicolas theory, it's discriminant D. So this implies that X is in CD. But here's the theorem of Hassett in his thesis. And that the converse holds that there's some restriction on D, which is that D is not divisible by 4, 9, or any odd prime that's 2 mod 3. And I don't know about you, I find this a bit horrible the first 50 times I saw it. It turns out to be saying that D is the norm of a primitive vector in the A2 lattice, if you like that. Or maybe more relevant for us today, it says that -3 is a square mod D. So there exists, I'll write this in a little tangentious way, there are integers x and y, such that x squared minus 2dy is minus. So of course this is easy to check just by looking at the thing, but this is, if you know quadratic reciprocity, that will speak to you.
These dimensions are like.
Yeah. Al is. Yeah. Oh, sorry. Have I said something stupid?
21? No, just in LS. H for primitive x is dimension 22, right?
22.
And the other one is.
Yes. Sorry, I'm thinking of the algebra of the middle part. Yeah. Thank you. Thanks. Right. Yes. Right, so now we understand which ones are these. And mostly which ones are these. And so I claimed that if X is birational to the Hilbert scheme of points on a K3, then it's easy to see this. So let me say something about Y. So now I need to tell you something about Hyperkaler manifolds. So if Y and Y prime are both deformation equivalent, I'm going to tell you absolutely the simplest case of Verbitsky's Torelli theorem, which is this one. Well, then H2 of Y Z. So these are fourfolds. They're Hyperkaler fourfold. H2 of YZ admits a quadratic form Q, and it satisfies this Q of alpha squared is alpha to the fourth quadratic form Q, such that alpha to the fourth is Q of alpha squared is 3 Q of alpha squared for all alpha. 3. So it's not at all obvious that this should be a quadratic form, much less integer value, but it is. By Bovil and Fujiki Bogomolov. This is called the Bovil-Bogomolov form. Verbitsky likes to put in Fujiki's name too. And then the theorem. Theorem of Verbitsky and refined by Markman is that y is birational to y prime if and only if h2 of yz is isomorphic as Hodge structures with this pairing to h2 of y prime.
So what is Marxman's requirement?
What's Markman's contribution? So I'm telling you this in a very in a misleading way. It's a standard fact that if y is birational to y prime, then these are Hodge isometric. Verbitsky tells you can go the other way if your Hodge isometry is given by a monodromy operator. Markman tells you what are the monodromy operators for Hilb n of K3, and for 2, it's all of them. Let's see, is it better to keep the diagram of these or the diagram of qubits? So Bovil and Donaghy, remember what we're trying to show is that if the variety of lines is birational to a Hilbert scheme, then X satisfies Hassett's cohomology criteria. So Bovil and Donaghy tell you that let's look at the primitive H2 of this variety of lines. So this is just the orthogonal to the Flipper class. From the Grossmanian 2.6. That this is Hodge isometric. So with its Bovil-Bogomolov form, it is isomorphic to the primitive H4 of X. And the isomorphism is via the obvious correspondence, via the universal Y. So what about H? So yes, we can understand birational geometry of these in terms of H2. Now you understand H2 of the variety of lines. Now let's understand H2 of the Hilbert scheme and of the moduli space of sheaves. And so H2 of the Hilbert scheme is this, maybe I think we've even heard this week, is generated by delta, which is half of the exceptional divisor, giving you non-reduced pairs of points, plus H2 of K3. And I guess I should tell you that Q of G is 6, and Q of delta is -2. So if I have, if F is birational to the Hilbert scheme of 2 points on K3, right, then I have primitive. I have H4. I'm sorry, I should have put a tangent. I'm sorry. I have primitive H4 of x contained in H2 primitive of f contained in H2 of f, which equals H2 of Hilb which contains H2 of the K3 in this way. And, you know, I totally confused myself. So you have you take this, intersect G perp, right? It can't be, right? So you take this piece, intersect G perp over here, and you get something codimension 1. H2 K3 intersect G perp has dimension. So this was, we just said this was dimension 22, so this is dimension 21, which is exactly what we want. Because, well, G can't be contained in Z delta because G is positive and delta is negative. And actually, Hassett and so I get some codimension 1 sublattice, right? This is some codimension 1 sublattice of H2 of the K3. And thanks to Voisin, we know that it doesn't contain any -2 classes. And so it's really the primitive cohomology of some degree DK3. Right? And so if f is birational, let me just write it. If f is birational to Hilb 2 of K3, then H4 primitive x contains H2 primitive of degree D K3. That's 1. And Hassett shows you that then D, it has to be, you can't just get any old D this way. It has to be of the form 2n squared plus 2n plus 2 over a squared. And if his last condition was inscrutable, then so is this one is even more so. If you like the old condition, this is now there exists x and y such that x squared minus integers, x squared minus 2dy squared is -3. So you can solve this Pell type equation.
So last time it was y, now it is y squared.
Yep.
That's
Yes.
the difference.
Exactly. So you can see that this is stronger than the old condition. And it's strictly stronger. So you see, well, you could check. 14 satisfies both conditions. You check up to about, there's a table in my paper. You check up to 100 and you find 3 or 4 numbers that satisfy the first condition but not the second one. The first one is 74. You write a computer program, you check up to d equals 1,000,000, and you find that of the d's that satisfy the first condition, about 2/3 of them satisfy the second condition.
2/3 do satisfy.
Do. Yes. Well, I think it's fair to say that well, let's take the theorem I haven't finished telling you about. Among Hassett's special divisors, you know, there are some that satisfy this, and about 2/3 of those are of this type. Up to 1,000,000. I think it gets, the density gets less, probably goes to 0 as you go to infinity, but it goes very slowly.
Why do you think it goes to 0? Why do you believe it goes to 0?
Experimentally.
Experimentally it goes to 2/3.
No, at 1,000,000 it was at 2/3, but at 500,000 it was more than 2/3. It's sort of going down very slowly.
How do you know that it goes to 2/3?
Yeah, it's a conjecture. Okay, now what do I want to say? I want to tell you about how I proved my own result. I want to evangelize a little bit about this. Let me say from here. This is always good. Stay from there. So I'm going to call this condition 3 stars. And I'm going to call the old condition, which is not on the board, the old condition 2 stars. Oh, I should say Hassett proves more than this. He proves that if D satisfies the second condition, then the generic cubic in that divisor has the variety of lines isomorphic to a Hilbert scheme. And he works very hard. And he gets this incomplete result. But now we have Verbitsky-Torelli, so Markman, Verbitsky-Torelli, and so we can do it all with lattice theory and not work very hard at all. So I want to tell you about the Mukai lattice. The Mukai lattice. For K3s, and then for Kuznetsov's category. So for K3s, this is a famous thing that you all know. Homology of a K3. I guess it's H tilde. This is H0. In my heart, I want to do everything in weight 0, but for everyone else's sanity, I'll do it in weight 2. So it's H0 twisted by -1 plus H2 plus H4 twisted by 1. And so this has a pairing on it. The pairing is the usual one on here, and then this gets paired with that by the intersection pairing. And you have a map to this from the topological K theory of the K3 surface. So normally this is, and I want to, it's the Mukai vector. So E goes to the Chern character of E times the square root of the top class of the K3 surface. And normally this would just take values in rational even cohomology, but with K3 surfaces you get very lucky, and it gives you, it lands in integral cohomology, and in fact it's an isomorphism. And the theorem of O'Grady, and maybe the honest hyperkaehler people in the audience can help me. To whom should I attribute this theorem? That H2 of the moduli space is V-perp. To O'Grady and Yoshioka and Boville and Mukai. This is a political question, right? O'Grady, Yoshi, and many others. So let V be in here. The Mukai vector, an algebraic Mukai vector. And so the degree 2 part is 1, 1. And let such that the moduli space of sheaves with Mukai vector V is smooth and compact. No singularities, there are no properly semi-stable sheaves. We have a good handle on when this happens. Then H2 of MV with the Bogomolov pairing is isomorphic to V-perp in H2. Right, so you have this rank 24 lattice. This is Z24 with the pairing U to the 4th plus minus E8 squared, where U is 0, 1, 1, 0. And E8 is what it is. Some E8 is some positive definite unimodular lattice. And so, what does Markman really tell you? So Markman, as you vary, so if Y is deformation equivalent to the Hilbert scheme of n points now on the K3 surface. Well, I should say I need the dimension to be greater than 2. I don't want to get another K3 surface, so we have to say something different. Well, always you can embed, well, of course, you can embed H2 of Y into U to the 4 plus minus E8 squared. So you can do it for the Hilbert scheme, and so you can do it for any, cohomology doesn't change when you deform. But Markman tells you there's a preferred embed. Of course, you can imagine as you deform around in the whole family of hyperkahlers, you might come back with a different embedding, and he picks one that's monodromy invariant up to the sign, well, up to something minor. And then the real theorem of Markman is that so the real theorem is that this is Markman and Rubitsky is that y is birational to y prime if and only if there exists a Hodge isometry that extends to the bigger Mukai lattice. In this preferred embedding. So it looks, what's the picture that you're seeing? You have, I made this period domain earlier. You have this period domain. I think this is a philosophy that's clear to all the experts, so I guess I'm trying to explain it to the students. We'll see if I'm succeeding. You could make the period domain B, which is a set of all lines. So let's put lambda to be this u to the fourth plus minus E8 squared, with which is Z24 with some pairing of signature 20, 4, or 4, 20. And I could look at B as the set of lines C sigma in projectivization of lambda C, such that sigma squared is 0, sigma bar is positive, modulo automorphisms of lambda. And I want to call this the derived period domain.
So you already used T for another period.
The derived. And we have a map from K3 surfaces to here. Which sends K3 to its Mukai lattice, right? And Orlov's Torelli theorem says that two K3s are derived equivalent if and only if their Mukai lattices are Hodge isometric. The classical Torelli theorem says that two of them are derived equivalent or are isomorphic if and only if there's an isomorphism of their H2s. But if you can extend it to the whole, if you take the whole Mukai lattice instead of H2, then you get a slightly weaker condition, which is derived equivalence. And I also want to make a map. I should say always what's the image? It's the sigmas such that the orthogonal to sigma intersect lambda contains a copy of U, which is just supposed to be H0 plus H4. So H0 and H4 always give you a copy of the hyperbolic plane. I shall tell you 0, 1, 1, 0. So it's some codimension 2 locus. Right? This is a 20-dimensional moduli space. No, 20-dimensional moduli space. This is 22. Also, for cubics, mapping to here, cubic fourfolds, they also have a Mukai lattice, which now I should talk to about. So Mukai lattice cubic, I'm going to call it somewhat tangentially K top of AX. And I define it to be the set of, well, it's the orthogonal to O1 and O2 in K top of the cubic. Orthogonal. And you can, it's easy to see that if AX is equivalent to an honest K3, then this Mukai lattice, sorry, with the Euler pairing. And with the Hodge structure pulled back from the even cohomology of X, Q. Because of course when you tensor this with Q, you get a good old cohomology. And so it's easy to show that if AX is equivalent to a K3 surface, then this is Hodge symmetric to the Mukai lattice of the K3 surface. So what do I want to clarify all the Beauvais stuff about the about H4 of X and H2 of F. So in AX, you always have two classes. You can take the structure sheaf of a line and the structure sheaf of a point, and you can project them down into here by these mutating past O01 and O2. Graham Schmidt, if you like. So that's completely unreasonable. So all you have the projection of O of a line and the projection of O of a point in AX. And actually, it's more convenient to take, lambda 1 to be the class of the projection of O line of 1, and lambda 2 to be the class of the projection of O line 2, but you see these span the same subspace, right? And these are in K top. And so what do we know? So lambda 1 and lambda 2, they span a copy. I want to take minus the Euler pairing, sorry. They span a copy of A2. This one in K top. So in this picture, the image, I'm sorry I erased it, the image in this period domain, is that sigma C squared 0. You get some other codimension 2 locus, orthogonal to this, to your favorite copy of A2 in that lattice. You actually only get an open subset of it, but that's okay. And now what can we say? So Richard and I proved, the fact is that H4 primitive of the K3 is isomorphic via the Mukai vector to lambda 1 and lambda 2 per in K. And the new fact, old fact in my paper with Richard, the new fact in the paper that I'm talking about today, which is about a year old, is that...
Sorry, are you speaking about H4?
H4, yes, I should specify one, right?
Should be
Of cubic.
Of the cubic, thank you. Right, so maybe to back up for a second. You have this non-unimodular lattice of discriminant 3, but it's even at least. You can embed it into H4, which is which is unimodular, but now it's odd and you're a bit unhappy. I'm saying you should embed it into this unimodular lattice of rank 2 more. And now it clarifies what this has to do, like how this connects to modular spaces of sheaves. The new fact is that H2 primitive of F is isomorphic to just lambda 1 term in K copy. And this is completely consistent with the O'Grady theorem and with Kuznetsov and Markushevich's theorem, which says that F is a moduli space of objects in AX with class lambda 1. Right, so this, and how do I prove this? I just take the Vogel-Donati fact about using the correspondence to get. Oh, sorry, not primitive. Primitive is that. Yes. The whole H2 is that. So I take the Vogel-Donati thing about the primitive ones, and then you have one more little thing to check, and you do a little calculation, but I think it really clarifies what you're looking at. And then I should wrap up. We all have a train to catch. But the lattice theory ingredients are show that X is in CD for some D satisfying Hassett's condition that says there's a guy in cohomology. If there's a K3 surface showing up in cohomology. If and only if there's a copy of the hyperbolic plane in the, let's call it the 1-1 part of K copy, which is the same as K, the numerical K theory of AX. And then you also show that for any hyperkaehler, there is a copy of U in the Markman-Mukai lattice if and only if the thing is birational to a moduli space of sheaves on K3. But it's purely lattice theory, right? You know in the Markman lattice of any moduli space, well, for any moduli space, the Markman lattice is the Hodge, is the Mukai lattice of the K3, and that contains a copy of U given by H0 and H4. And then you show that X is in CD for some D satisfying the Stronger condition. So this is birational to a moduli space of sheaves for some D. It's in there if and only if some slightly pain in the ass characterization in terms of the lattice, but saying that there's a vector, there's an isotropic vector that dots to V to give you 1. Just like if V were the ideal sheaf of n points, you would take the other vector to be 1 point. If and only if that is birational. And now there's in 1 minute, you ask yourself, are Hassett's qubits containing a plane in another cycle, do they all satisfy this condition? And experimentally up to D equals 100 it seems to be true, but in general there's some purely number theoretic thing that no number theorist that I've talked to seems to know how to settle. I meant to write that condition up, but I see I'm out of time. Questions?
So that means you're suggesting other building the rationality to be equivalent to that stronger condition.
I have one. Galkin and Shinder suggests. I have no idea about rationality anymore ever since last week. It does suggest, there's another codimension 2 locus in here that's looking like it's to do with the Gushel Mukai varieties, fourfolds that they're talking about. and EPW subspace. And of course, you'd like to have some category for every point in this modulo S space. And Paul Aspinwall has some stringing speculation about that. Let me not repeat that until we see whether it's really working.
Any other? Oh, yes?
I mean, very quickly, Nicolas Addington has a notion of hyperkaler which I could be in type, and it's a notion on the lattice. Do you know how it fits in this picture?
I don't know off the top of my head. Well, I should say, Lehn showed that there's if it's in CD for some D not divisible by 4, then it has a decomposition of the diagonal to tie in with the rest of the components. Maybe we can talk about the trade. Okay.
Let's thank Nick again.
Let's also thank the organizers for putting together this.